Hello everyone, I am Lisa Poirier-Beck and today I'm going to present you the work I did during my master internship, supervised by Olivier Breton and David Fofi at the Vibot laboratory. This is about 3D reconstruction of mirror-like surfaces by smart deflectometry. So let's start. Nowadays, a lot of industries need to reconstruct specular surfaces in a fast and accurate way, but the main problem of deflectometry is the calibration process. With this information, we propose in this work a new deflectometry approach based on light field principle. First of all, I'm going to present the background with the definitions of deflectometry and light field. Then I will go through the methodology followed by the experimental setup and the results. So let's start with the background and the definition of deflectometry. Deflectometry is a set of techniques to reconstruct specular surfaces in 3 dimensions. Firstly, I will talk about the shape from distortion, which is a deflectometry technique based on phase measuring between a projected and a reflected pattern. This picture completely illustrates this technique. To improve it, Tarini used an RGB pattern to consider multiple patterns in a single one. The main drawback of shape from distortion is that the calibration of the light source is very difficult since it is a plane object, like for example an LCD screen. Now let's talk about the directory measurements, which is another deflectometry technique. It is based on the computation of the direction of light rays using the light field principle. For example, Koutolakos and Steger used 2 planar targets to recover 2 positions of a single ray and then obtain its direction. They proceeded to triangulation between the camera, the targets, and the mirror. Another example of method is by Tin, who uses screen with predefined polarization states. So the main drawback of direct ray measurement is also the calibration of the light source, still because of big plane light objects. So now, what is the light field principle? Light field is a way to conceptualize the direction of every light rays in space. It is mathematically defined by the plane optic function, which is defined by 2 parallel planes with 2 Cartesian coordinates in each plane. This picture here illustrates the concept of plane optic function. Nowadays, light field is mostly known by the popularization of the plane optic cameras. In this work, we point our attention on the plane optic illumination function, which is in fact the light field principle applied to the directional light sources. Indeed, the plane optic illumination function is defined by the radiance in the direction of the light ray, the viewpoint, and the viewing direction originated from the viewpoint. So more intuitively, the concept of the plane optic illumination function is that the intensity of a light ray depends on its direction. Based on all this information, in this work, we propose an extension of the light field illumination principle. The wavelength of a light ray depends on its direction. It could be done using a reflective diffraction grating with known ray properties and behaviors thanks to optical formulas. This concept is interesting since the wavelength does not vary with intensity of light. Then the small light could be considered as the point, and this could ease the estimation of the position of the light source of the system in deflectometry. Moreover, the properties of direction and colors of ray are already defined by well-known optical formulas of diffraction. Now I'm going to present the methodology, and first let's see a visual representation of the principle of our work. The white light emanating from the light source is directed to a reflective diffraction grating, or at least an object that could diffract light into multiple color values like wavelengths. Its color light ray will be reflected in the mirror object, and depending on the camera's position, the camera will capture only one colored ray from the reflection in the mirror. In the following slides, I will explain how it is possible to get the angular position of the mirror by capturing this color value. So first, what is already known in our system? The position of the camera, the focal length of the camera, the position of the grating, and the behavior of orientation and color of rays of the grating. And what we miss, what is unknown and what we want to find as a result, is the point on the surface of the mirror where a reflection occurs and the normal line of the mirror at this point. So here we have a representation of our algorithm with in green the output parameters, what we want to find, and in blue the input parameters. In other words, the light source information and the camera information. I will go through all the details starting with this first part of the algorithm, which finds only the 2D representation of the results, and then I will go to the second part which gets the full 3D representation of the results. So once the image is captured, we proceed to hue detection by converting the RGB image into the HSV domain. The V component allows us to get the most brilliant pixels, which are in fact the reflected image of the light source, and the H component is to get the hue value of the reflected color. Then we define the hue value and position of the reflected ray with two methods. Firstly, by computing the mean hue and the mean position of colored pixel. Secondly, by assigning the hue value of a pixel to its position. Then here goes the calculation. First, knowing the position of the grating and the camera, we are able to calculate the D1 equation and the L1 distance between those two objects. Then knowing the hue value captured by the camera, we are able to define the D2 and D3 in line 2 and line 3. And then once we have all this, we can easily find the coordinates of M, the 2D coordinates of M, which is the point at the reflection in the mirror. And in fact, we can also have the normal line, which is in fact the bisector of the third angle of this triangulation. So now we have the 2D coordinates of M. We can get the third axis, so the 3D coordinates of M, with the second part of the algorithm. So to do this, we need to turn the grating of 90 degrees, get the new hue value captured by the camera, and get the new ray angle of a 4 from the grating, and we rotate the point M and the bisector along the new axis with the new angle alpha 4. Following this procedure, we can get the 3D coordinates of M, the reflection point in the mirror, and the normal line at this point. So this was the concept of our system. Now let's talk about the calibration. First, we get the intrinsic and extrinsic parameters of the camera using the famous Zhang's method. Then, to get the position of the light source, which is here represented as a point, we capture its reflection into a mirror placed at the center of the checkerboard pattern. Then, we move this pattern into different pattern positions to get different color rays all coming from the light source. And thanks to Zhang's method, we are able to compute the normal line of the pattern at the mirror position. Then we need to rotate the ray from the camera of 180 degrees along the normal line to get the incident ray. And finally, the intersection of calculated incident ray is the position of the light source. And that's how the calibration process is done. So now let's talk about experimental setup and results. For a question of time and for the exceptional teleworking situation in all the world, we evaluate the system by simulation using the 3D computer graphics software Blender. To represent the reflective diffraction grating, we have created and used a pinhole light source. Depending on the viewpoint, the perceived color changes. Plus, we made our simulation system based on the most possible on reality in order to estimate some noises or errors that we could encounter in a real system. First, we did the simulation of the calibration pattern. These images show here that it is possible to create such a pattern and visualize the reflection of the light source for different positions of the pattern. Of course, the calibration method will have to be evaluated when the real system will be constructed in a further work. So here are some photographies of our results for a mirror plane object and a mirror sphere object. The reconstructed point clouds are blue and the normal line are green. We reported the point clouds error in a table, and the first thing we can see is that the method number 1 is better than the method number 2. We used to think the contrary because theoretically our method is a ray by ray, but in practice it seems to be a beam by beam. And moreover, even if the results are very similar to reality, as you can see in the table, we have to consider some errors. First, we remark that the errors of the sphere are higher than the errors of the plane. And we made the hypothesis that there is a distortion of the perceived color due to the curved surface of the sphere. Indeed, the geometric distortion could lead to an unintended range or separation of the colors. Plus, we have to consider errors due to calculation. Indeed, the root mean square error varies from 0.1 to 0.7 degrees during the linear regression of the behavior of light source rays. By the way, thanks to simulation, we are able to observe the normal line, here in green. And by observation, their correct behavior among the tested objects validate our method. For example, for the sphere object, we can see that they all meet in the center of the sphere, which is here represented as a pink point. And for the plane object, which is here represented as a pink line, we can see that the normal lines are all parallel to the mirror, which is very coherent since the mirror is a plane object. So, to conclude this presentation, in this work, we propose a unique 3D reconstruction method for specular mirror-like objects by triangulation using an RGB light source which follows the light field principle. We have provided a simple way to calibrate a deflectometry system with a new light source and a new calibration method based on the well-known Zengs. We also integrate the light field as a solution in deflectometry that studies RGB in a different manner than other RGB methods, like the method of Tarini. And our first experimental results are encouraging and validate our proposed approach. Some limitations are errors due to the nonlinear behavior of direction and color of rays of the light source. We have also seen that it is preferable to compute the mean color value of detected colored pixels, since our ray-by-ray approach is in fact a beam-by-beam in practice. And during this work, we have met the hypothesis of a color distortion caused by the surface of a curved object. This hypothesis could be verified and solved in a future work. Speaking about future work, we would elaborate a real system by leaning on the established simulated system and evaluate its limitation and capacities in the real world. We would also explore different light sources, like, for example, using the reflective diffraction grating, or constructing a pinhole light source, or any other light source. And finally, it could be interesting to investigate the possibility of integrating a light field camera to our system, which would make a full light field system. So here are some references I used to study this subject, and thank you for your attention.